Hi everyone, today I'm going to present our recent work, a hierarchically integrated framework for resilient task allocation and planning in heterogeneous multi-robot system. Let me begin with an overview of the framework architecture. It consists of two main layers. The first layer includes both task allocation and the path planning. The second layer is a mid-level coordinate manager, which is responsible for managing execution level issues in real time. In the task allocation module, we consider both heterogeneity of robot capabilities and the diversity task types. The task cluster process is informed by a cost map that accounts for obstacles in environment. This helps ensure that tasks separated by significant barriers, such as walls, are not clustered together. For path planning algorithm, we apply the D-star algorithm, which is well suited to dynamic environments. Unlike traditional approaches that rely on grid-based map, we are using an adaptive Houghton sequence to generate in the planning space. I will talk into details on this component in the upcoming slides. The second layer of the framework is the coordinate manager. This component monitors the system during task execution and addresses issues that arise in real time. A system compiler aggregates data and observes task progress, while behavior trees are used to manage reactive strategies. This include responses to agent failures, blocks paths, and other unexpected events that may not addressed by high-level planner. Now, let me describe the obstacle-aware clustering approach in more detail. We define a set of cost rules to penalize grouping tasks that are separated by walls. There are three types of penalty. First one is the wall center penalty. The tasks near the center of the wall may require significant detours to get in the other side of the wall. The second penalty is the junction penalty, which is intersections between the walls are likely to cause deadlock. And finally is the map edge penalty. If a wall is connected to the map boundary, robots cannot get through it. To incorporate these penalties, we draw a straight line between each pair of tasks and add cost wherever the line intersects a wall. This discourages the algorithm from clustering tasks that are difficult to reach from one another. So in the left figure here, you can see the result of clustering for a single task type. In the right figure, which includes multiple task types, tasks are clustered separately even if they are close together but divided by a wall. Let's move on to the path planning component. As mentioned earlier, we use an adaptive Houghton sequence map. This technique adjusts point density based on obstacle distribution. More points are placed in cluttered area and fewer in the open area. This resulting triangular mesh allows smoother and more efficient paths compared to conventional grid world maps with axis-aligned squares. In our preliminary experiment, we applied 4 robots and 18 tasks. The robots represent in this colored circle, and they will collect items at blue squares and deliver them to a green square. When a robot turns orange, it indicates the completion of its current task and readiness for the next. And the red walls here are unknown walls. When the robots want to get through it, it cannot, and then it will ask for a replan. We also conduct some experiment on heterogeneous robot team. These red circles are turtleboat, which are ground robots, and the blue circle are drones, which can fly over the green area. The green areas are bushes. We also conduct some experiment with unexpected scenarios happens to test how the system can recover from this failure. This one is for robot failure. And this one is for task failure. We also use Isaac Sim to test our results. As for our ongoing work, we are integrating the system with a simulated human mental model to represent operators' expectation. When the actual system's behavior significantly deviates from the model's prediction, it triggers a report to the human operator, who can then adjust the system. This human-in-the-loop design further enhances the system's resilience, especially in safety-critical or uncertain environments. Thank you.